For me to get back. All right, so we missed, what? We missed the very beginning of this video. Just run through it real quick so Kaylin has it. Basically, the difference between the chemical reactions and nuclear reactions is that the nuclear reactions are in the nucleus, right? So we're changing protons, neutrons, and elements are changing into new elements. Energy changes are really big with nuclear reactions, not quite as much with chemical reactions. And protons to neutrons, they have to stay in the nucleus somehow, and there's a strong nuclear force that keeps them there even though the protons are repelling each other, and it takes neutrons in the nucleus to kind of keep them together. There's a belt of stability where the proton to neutron ratio is important, and if it gets out of whack from that proton to neutron ratio, then they're going to automatically decay. When they're smaller elements, they like a 1-to-1 ratio. As you get to larger elements, it takes more and more neutrons to make it stable. And then when they're not stable, they decay naturally by emitting particles. So the most common types of radioactive decay are alpha, beta, and gamma. Have you heard of alpha, beta, and gamma before?
Yes.
Probably heard of it. Do you know what it is?
They're radioactive.
It's radioactive stuff that comes out that is not good for you, right? Yeah, these are the things that kill you, right? So, they're also the things that change, yes, your superpowers. All right, so alpha particles are basically helium atoms is really what they are with no electrons. So a helium atom, 4/2 He, that's an alpha particle. Or sometimes it's, sometimes it's also written, dang it, what did I do? Oh, I'm hitting both screens, that's the problem. I'm going. I hit the button on the bottom. All right, so there. The helium atoms are the alpha particles.
Is it specifically helium?
Yeah. I mean, it's got 4 neutrons. I mean, it's got 2 neutrons and 2 protons. Right? Because it's 4/2. Doesn't have any electrons, so it's a helium nuclei, basically.
What happens to the electrons?
Okay, here's where you get confused because the electrons are, these things are happening in the nucleus. The electrons aren't there. So these particles are, the protons and neutrons that are in the nucleus are spitting out these things. So it's not spitting out an electron. It's spitting out basically a helium nuclei without the electrons. So it's just going to have to pick up electrons from somewhere else. But anyway, you can write it either way. You can write it as a helium or you can write it with the little alpha symbol. It's fine. So here is an example of a nuclear reaction with alpha emission. So emission or decay, right? Emission means it gives off, so the alpha particle is in the product. Notice what happens to the uranium. What does it change into? TH, which is thorium, right? I'm pretty sure that's what, yeah. So 238, this is the mass number. Notice that 234 and 4 add up to that 238. Notice that 92, the 90 and the 2 add up. That's as hard as this gets, by the way.
So it changes it and just it adds however many helium. Okay, got it.
Right, because these things basically came out of that nucleus. So the nucleus of the uranium atom spits out a helium nuclei, and the atom now changes into thorium. What?
Wait, I thought atoms couldn't change. So
They can in nuclear reactions. They cannot in chemical
Why
reactions.
don't we change like stuff into gold then?
It's not as easy as it sounds. All right, so here's your band of stability again. I don't know why our projector's so dim, but it is. If nuclei start to fall above that line, they have too many neutrons. So they want to get rid of those neutrons, and they do that by emitting a beta particle. Okay, so now your question is, what's a beta particle? What does a beta look like? What is that? Okay, what particle has 0 mass and a -1 charge?
Oh, electrons.
An electron. Where did this electron come from, though?
The helium.
The nuclei. It came from a neutron. A neutron inside the nucleus basically spit out this particle. I never realized it's weird. So the neutron can now change into a proton because what did it kick out?
The electron.
It kicked out a negative charge, so now that neutron now has a positive charge, and now it's a proton. So it changed the ratio of protons to neutrons. It also changed the element.
So neutrons are made of protons?
Well, that's getting into quantum physics, and no, they're leptons and quarks and blah, 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 blah. But those, yes, in essence, those subatomic things, those particles inside neutrons and protons can break down and split into other things. And let's just leave it at that, because I don't know the quantum mechanics vocabulary well, and I'll confuse you. Yeah, I actually never had a quantum mechanics class. Chemical engineering didn't require quantum mechanics. But it's funny because I'm teaching the AP Chem, but Miss Ainsworth, and I've had like thermo classes and all that. She hasn't had thermo classes, but she's had quantum mechanics, and she's teaching the AP Physics. So those are some questions you can ask her, but she may know it more off the top of her head than I do. But the reality is yes, neutrons and protons have smaller particles. Those smaller particles can be rearranged and spit out in different ways. If you spit out a beta particle, you in essence change a neutron to a proton. Okay? And you can again see that this 131, it's still 131 plus 0, 53, 54, and negative 1. Okay? That's our balancing of the nuclear reactions, by the way. Okay?
This why I have a heroin addiction.
All right. There are other particles. There are positrons. There are neutrons. There are electrons. There are protons, right?
I
didn't make it up. All right.
Sounds like
So Megatron is a positive.
Are we gonna learn about Megatron?
All right. So besides our superheroes, all right. So there are other particles. When they're below that and they have too many protons, they tend to become stable by positron emission or electron capture.
Miss Robinson, that's a bit below the belt.
All right, so what happens in a positron emission? A proton, basically, it's the other way, turns into a neutron, and a positron is emitted. So there's your little positron. Anyway, you can still see. This one is gamma. We're going to talk about the gamma, and we're not getting into matter and antimatter. There's a whole world that we're not getting into. So
you can go from magnesium to sodium, but you can't go from
Dark
like
matter.
aluminum to gold.
yeah.
Well,
All right.
aluminum.
There's like, so this one's an electron capture. So where's the electron?
Capture. React.
On the reactant side, because it captured it, right? So now this one did catch an electron from outside and basically captured it into the nucleus.
Wait.
Yeah, not as easy. Yeah, and we're not going into the details. All right, gamma particles. Gamma particles basically end up in all of them. If you have a nuclear reaction, you almost always have gamma rays. Gamma rays are what they shoot at you for cancer and things like that. When they shoot radiation, this is what they're shooting, which is very radioactive. It's a lot of energy. This is your initial big energy change. So those, we don't really, it's when you balance nuclear reactions, we don't usually ever write the gamma rays in there. You can, but they're zeros. They don't balance into your stuff because they're 0, 0, right? They're just energy. So we don't usually always write them.
How do we know they exist? This is 0 over 0.
Because they can measure the energy. And of course, if everything has energy, right? Go back to your dual nature of light. It's got to have wave properties and particle properties. So there has to be a particle. So the particle is a gamma particle. Okay, so basically, the short version is that nuclei greater than 83. So when you get to about 83 on the periodic table, what do you start noticing about the masses? Yeah, you start getting parentheses. Why do you think you get some parentheses?
There are no stable gamma with an atomic number greater than
They
8.
gay.
They're not stable, so they don't stay around very long for them to measure their masses as accurately. So those are good estimates of their masses. But anything over 83 starts to be is radioactive and will naturally decay. So have you heard of them doing radon sensors in your basements and stuff? We don't really have basements here, but they do that because it's radioactive decay from the ground, and so it happens naturally. And it gives off these particles. So, okay, balancing nuclear reactions. This is a skill you need for the AP test. It's easy, right? All we're doing is making sure the tops balance and the bottoms balance with the numbers. That's all there is. That's it. That's all there is. So let's look at this one. What would go in the blank?
Negative.
An electron.
Beta.
Beta.
A beta particle.
Beta.
Because the top already has the 14, right? And so we need 0 over here, and we need a -1 so that -1 plus 7 is a 6. Agree?
That was difficult.
Okay, this is for one of those clicker questions, and I'm not pulling that mess out. All right, what's going to go in that blank?
Neutron.
A neutron.
Are we gonna get all those every time?
Yeah.
Like the alpha, beta,
Can you read
positive.
that?
So this is just
Oh, will you
basically
get these
basic math.
choices every time? No.
Wait, can you?
But,
I'm just gonna
Let's
write
just
down the
make
little,
this our test.
like which
I'm
one
sorry,
it is,
but
like
positron
the
still sounds
Symbol.
thing is.
okay, you're getting ready to do it. You're getting ready to practice it.
Let's just make this our test and just call it a day.
2 minutes. You can go if you need to go.
Make it like 60 questions after this.
Yes.
All right, so we understand the balancing, yes?
Yes.
Do we need to do one more? We're good. Think we're good? Okay. This is your little worksheet. I want you to do it in 5 minutes.
Is this
Oh
test
my
good?
God.
I have a question.
Yeah, just the front.
Are we gonna do our
Calendar and
what is are we gonna be doing
So
the Arrhenius equation?
the Arrhenius equation?
Yeah.
Not today.
Uranians.
Are we doing it next time?
You don't actually have to ever
Is it
calculate
like we're
it.
gonna be
Just
like
do
using
one maybe test.
YouTube
I'll talk about it for you.
Yeah,
What
make sure
a
you
waste,
stop
let's
the
go to
recording
soup.
too.
don't ever have to calculate it. What you just have to
Yeah,
do
here's
is
those
the
gamma
rate constant.
particles.
Coward, you have to taste it for yourself.
Make sure you stop the recording too.
But it is a way to
Yeah.
get to activation and stuff. Okay, so I'll pause the video there while y'all work on that. So that or sharpen pencils.